For most of human history, the night sky appeared eternal and unchanging. Stars seemed fixed, galaxies invisible to the naked eye, and the idea that the universe itself could evolve was inconceivable. Only in the last century did we begin to understand that the cosmos is not static but dynamic, stretching outward with an energy that carries galaxies away from one another. This expansion is one of the most astonishing discoveries in all of science, reshaping how we view our place in the vastness of space. To say that the universe is expanding is to recognize that everything, the stars, the galaxies, the very fabric of space-time, is in motion. The galaxies are not rushing through space like cars on a highway. Instead, space itself is stretching, and with it the light from distant objects is elongated, shifted into redder wavelengths. This simple observation, first made in the 20th century, became one of the foundational proofs of the Big Bang, the theory that the universe emerged from a hot, dense state some 13.8 billion years ago. The Big Bang did not simply hurl matter outward, it set in motion a process that continues today, with the cosmos still expanding, still cooling, still revealing its story through light that has traveled across unimaginable distances. For decades, scientists debated whether this expansion would last forever or eventually slow, perhaps even reverse. Gravity seemed the natural counterforce, pulling matter together while expansion worked to push it apart. Would gravity win, or would expansion? For much of the 20th century, cosmologists expected that the universe might one day stop growing and collapse in on itself, a fate known as the Big Crunch. But the universe surprised us again. In the late 1990s, careful measurements of distant supernovae revealed something unexpected. Not only was the universe expanding, it was doing so at an accelerating rate. This discovery introduced the idea of dark energy, a mysterious force that appears to push space apart more and more strongly as time goes on. If dark energy continues its work indefinitely, the universe may face a bleak heat death, in which stars burn out and galaxies drift beyond each other's horizons, leaving only cold emptiness. This vision of a universe stretching forever into darkness became the dominant model. And yet, the balance is delicate. Dark energy remains one of the deepest mysteries in physics. We do not know its true nature, nor can we be certain that its behavior will never change. If it weakens, reverses, or transforms into something new, the destiny of the cosmos could shift dramatically. Expansion might slow, then halt, and finally give way to contraction. Instead of galaxies receding into the abyss, they would begin to fall back toward one another. Over billions of years, the universe that once blossomed outward could collapse inward, retracing its steps toward a fiery, dense state reminiscent of its origin. This thought is both unsettling and fascinating. For a species that has only just begun to grasp its cosmic context, the idea that the universe might not be drifting into cold silence but instead rushing toward a violent rebirth challenges everything we think we know about existence. The story of expansion, acceleration, and mystery is only the first act. The deeper question, one that stretches beyond physics into philosophy and imagination, is simple yet profound. What if the balance shifted? If the universe were to begin contracting, the earliest indications would arrive quietly, buried in the vast flow of data astronomers collect each night. At first, the signals might look like small anomalies, galaxies not receding as fast as they should, subtle shifts in the spectra of distant quasars, a pattern in the cosmic microwave background that no longer matches the predictions of eternal acceleration. For decades, scientists have relied on the redshift of galaxies to measure cosmic expansion. The further away a galaxy lies, the more its light is stretched, shifted toward the red as space itself grows between us. If the universe began to contract, the change would not be immediate or obvious, but over time the redshifts of the most distant galaxies would cease to grow as expected. Some might stabilize, others might even drift into blue shift, their light compressed as they began moving closer rather than farther away. Such evidence would not come from a single observation but from long-term comparison. Astronomers track light from billions of galaxies, measuring their velocities and distances, building a tapestry of cosmic history. As contraction began, the statistical weight of their data would start to lean in a new direction. Perhaps a few galaxies in particular regions of the sky would be the first to show deviations. The universe is vast, and disentangling local motions from cosmic scale shifts would be a monumental challenge. Galaxies fall into one another's gravitational fields naturally, so how could one be sure that an observed blue shift is not just a collision in progress, but part of a larger, universal reversal? Only the accumulation of evidence across the entire sky, analyzed with exquisite precision, would begin to reveal the truth. The cosmic microwave background would offer another clue. This faint afterglow of the Big Bang permeates all of space, its pattern frozen since the universe was only 380,000 years old. It is like a photograph of the cosmos in its infancy. For years, scientists have used it as a baseline to measure expansion, mapping the way structures have grown from tiny fluctuations into galaxies and clusters. If contraction began, the background radiation would not remain perfectly static. Subtle distortions would appear, caused by the changing geometry of space-time. Anisotropies might shift in ways inconsistent with current models, hinting that the direction of cosmic evolution itself had changed. What was once a map of outward growth would begin to whisper of inward collapse. Inside the astrophysics community, such signals would spark fierce debate. For decades, the paradigm of an accelerating universe driven by dark energy has been supported by observation after observation. To suggest that expansion had slowed, much less reversed, would seem at first like heresy. Researchers would argue about calibration errors, about the reliability of instruments, about biases in the data. Teams would repeat the measurements, refining methods, upgrading telescopes, pointing them again at the same distant sources to confirm or deny the hint of reversal. Months would stretch into years, conferences would echo with arguments, and papers would clash in peer-reviewed journals. Some scientists would cling to the idea of acceleration, others would see in the data the beginnings of an epochal shift. As the evidence mounted, the broader public would begin to notice. News headlines would speak of cosmic contraction, television programs would feature astronomers hesitating before the cameras, admitting that the universe may not be what we thought. Religious leaders, philosophers, futurists, all would seize on the ambiguity, interpreting it in ways that reflected their own beliefs. To most people, the distinction between expansion and contraction would remain abstract. The stars would still shine, the planets would still orbit. But for those who understood, the revelation would be staggering. It would not be a minor correction in physics but a profound shift in our understanding of existence. In such a moment, humility would press heavily upon the scientific world. We would be reminded that our models are provisional, that the universe is not obligated to match our predictions. To detect contraction would be to glimpse the first tremors of a future we had not imagined, one where the cosmos does not simply drift toward cold emptiness but turns back upon itself. And as dramatic as that realization would be, it would not yet tell us what contraction truly means for the fate of stars, galaxies, or life itself. Detection would only be the beginning. Once the scientific community could no longer deny that the universe had begun to contract, the conversation would inevitably shift from detection to explanation. If expansion has defined our picture of the cosmos for nearly a century, contraction demands a new paradigm. Theories would multiply, and with them a fierce struggle to understand what hidden forces shape the fate of all things. The most immediate explanation would focus on dark energy. For decades it has been described as a repulsive force, a kind of pressure woven into the vacuum of space itself, pushing galaxies apart. Its discovery was astonishing precisely because it seemed to grow stronger over time, accelerating expansion rather than allowing gravity to slow it. But if contraction began, scientists might argue that dark energy is not a fixed property of the universe. Perhaps it is dynamic, evolving across cosmic timescales, like a field that waxes and wanes in strength. If it has now weakened, or even flipped in sign, its role as a driver of expansion would collapse into its opposite, dragging everything inward. This hypothesis would immediately inspire a rush of theoretical work. Particle physicists would search for mechanisms in quantum fields, cosmologists would attempt to fit the data into models where dark energy decays, and speculative thinkers would imagine transitions to states of physics entirely unfamiliar to us. Others would insist that the answer lies not in some exotic force but in the inexorable pull of gravity. Expansion has always been balanced against the mass of the universe. If the average density of matter is high enough, gravity eventually wins, pulling galaxies back together in a slow but relentless embrace. For decades, observations suggested that there was not nearly enough matter, ordinary or dark, for such a fate. Expansion seemed unstoppable. But if contraction is real, then perhaps the universe contains far more mass than we realized, hidden in forms we have yet to detect. Vast halos of dark matter, or even stranger particles invisible to our instruments, might tip the scales toward collapse. This scenario would push astronomers to redouble their search for unseen matter, scouring the cosmos for gravitational effects that betray its presence. And then there would be those who turn to the most unsettling possibility, that our fundamental physical laws are incomplete. Perhaps what we have taken as constants are not constant at all. What if the strength of gravity evolves with time, or the geometry of space-time itself can undergo phase transitions, shifting the very rules by which the universe operates? In this view, contraction would not be a simple reversal of expansion but the unfolding of a deeper reality. Some might even speculate that the cosmos is cyclic, oscillating between growth and collapse like a heartbeat, driven by laws we have only dimly glimpsed. Others might argue that contraction is a sign of instability, a prelude to the birth of an entirely new kind of universe. Outside the halls of science, the news would ignite equally passionate debates. For many people, the idea of cosmic contraction would carry echoes of myth and prophecy. Some religious traditions would see in it confirmation of ancient visions of destruction and renewal. Philosophers would seize on it as proof of the impermanence of all things, the ultimate validation of cycles of birth and death. Futurists might imagine it as an opportunity, speculating on whether advanced civilizations could ride the collapse into whatever comes next. Popular media would frame it alternately as a looming apocalypse and as a doorway to rebirth, amplifying the drama while often losing sight of the science. The scientific community itself would not speak with a single voice. Contraction would not immediately resolve into a neat explanation. Instead, it would fracture the consensus built over decades of studying acceleration. At conferences, old rivalries between theorists would reignite. Some would cling to the idea that the data are being misinterpreted, that the universe must still be accelerating and that contraction is an illusion caused by local effects. Others would argue passionately that contraction is the only conclusion, even if it forces a radical rewriting of physics. Graduate students and young researchers would find themselves caught between loyalty to established models and the excitement of exploring a new frontier. The culture of cosmology would shift overnight from one of relative stability to one of heated uncertainty. As this intellectual struggle played out, the larger question would loom over every discussion. Whatever its cause, dark energy reversed, gravity triumphant, all laws unknown, the fact of contraction could not be denied. If the cosmos was no longer expanding, then the future we once imagined had vanished. Gone was the prospect of an endless drift into cold emptiness. Ahead lay something else, something more violent, more immediate, and perhaps more final. Once contraction is accepted, The next question is survival. The first stages of contraction would not be felt in daily life. Earth would circle the sun as it always had, seasons would pass, and the stars would appear unchanged to the naked eye. Yet far beyond the reach of ordinary sight, the universe would already be shifting. Contraction would unfold on scales so immense that its early effects would reveal themselves only in the structure of galaxies and clusters. Distances between galaxies, once widening with expansion, would begin to shrink. Over millions of years, clusters that might have remained apart in an ever-expanding cosmos would start to drift together. What expansion had been pulling apart, contraction would now press back toward unity. At first, the changes would be subtle, galaxies approaching one another just slightly faster than expected, their motions curving toward one another as if bound by a tighter net. Over longer spans, the evidence would become undeniable. Neighboring galaxies that might not have collided for tens of billions of years would instead meet far sooner. The universe would become a busier, more violent place as contraction tightened the great web of matter. Collisions would multiply, reshaping galaxies into tangled knots of stars and gas. Where expansion had promised isolation, contraction would bring encounters. Within galaxies themselves, contraction would play a different role. The structure of a spiral or elliptical galaxy is defined by the balance of gravity and motion. Stars orbit their centers because the expansion of the universe does not dominate at such small scales. Their dynamics are already set by local forces. For this reason, contraction would not suddenly pull stars into their galactic cores. Instead, the galaxy's journeys through space would curve inward, carrying them toward one another more quickly. Star systems like our own would at first remain intact, bound by the gravity of their suns. Yet over time, the increased density of the universe would mean more gravitational disturbances, more near passes from wandering stars, more chances that planets might be tugged from their orbits or worlds flung into the cold between suns. The solar system would likely persist for a long while without obvious change, but contraction would alter its environment in ways that could not be ignored forever. As galaxies fell toward one another, the frequency of supernovae and energetic collisions would increase, filling space with more radiation and debris. Cosmic hazards would multiply. The sky, though still vast, would grow brighter with the light of merging galaxies, and eventually, over billions of years, the heavens would look crowded compared to their quiet emptiness today. This raises a deeper question: how far down does contraction reach? While galaxies and clusters are the first to feel its grip, physicists would wonder whether the shrinking of the universe might also touch the scales of atoms and particles. Space itself is the fabric in which everything resides. If that fabric contracts, do the threads of matter themselves tighten? The prevailing view in modern cosmology is that local structures, atoms, molecules, even planetary systems, are shielded from expansion or contraction by the strength of their own forces. Atoms do not stretch as the universe expands because the electromagnetic force binding electrons to nuclei is far stronger than the gentle stretching of space. By the same reasoning, atoms should not shrink when space contracts. But the question is not trivial. If contraction altered the constants of nature, if it reshaped the laws that govern the very small as well as the very large, then even the familiar ground beneath our feet might be transformed. Some theorists might suggest that quantum scales are immune, preserved by the self-consistency of physical laws, while others might argue that contraction could gradually compress all things, from galaxies to molecules, in a universal collapse of scale. Such debates would not be merely academic. If contraction reached into the atomic domain, chemistry itself could shift, destabilizing the matter from which life is made. The very concept of permanence would erode, and existence would begin to unravel from within. For now, though, the grand stage would be written in the heavens. Galaxies tightening, clusters coalescing, the architecture of the cosmos reshaped into ever denser forms, this is the visible drama of contraction's early age. Humanity, watching from a fragile planet circling an ordinary star, would not yet feel the direct pull of collapse. But we would look upward, measuring the slow but inexorable change, and recognize that the balance of the universe had tilted. The question of atoms would remain uncertain, but the question of destiny would already weigh heavily. But humanity looks to the skies and wonders about time. Time has always seemed like the most unyielding of realities. We wake, we age, we remember the past but not the future. The arrow of time appears absolute, pointing from order to disorder, from youth to decay. In physics, this arrow is tied to entropy, the measure of disorder that tends to increase in any closed system. The expansion of the universe has long been understood as a backdrop to this process, a stage on which entropy could play out without limit. But if the universe begins to contract, the very foundations of how we understand time come into question. Does the arrow reverse along with space, or does it continue forward even as the cosmos folds inward? Philosophers and physicists alike would grapple with this puzzle. One line of thought suggests that contraction could indeed flip the arrow, forcing events to unfold backward, memory itself to dissolve, and causes to follow their effects. In such a universe, the collapse of stars would play in reverse, light would grow more concentrated, and beings like us might relive their histories in reverse sequence without ever realizing it. This is a strange and deeply unsettling vision, one that presses the imagination to its limits. Yet most physicists doubt such a literal reversal. The laws of motion in physics are symmetric. Mathematically, many processes could run forward or backward, but entropy gives time its one-way quality. Even in a contracting universe, the accumulation of disorder seems destined to continue. Stars that collide will not collide, shattered worlds will not reassemble. The march of entropy is indifferent to the direction of cosmic expansion. Still, contraction reshapes how we think about entropy itself. In an expanding universe, entropy increases by dispersal, energy spreads, stars cool, galaxies drift farther apart. In a contracting universe, the same principle applies, but the conditions change. Matter and energy no longer spread out indefinitely. Instead, they are drawn together, crowded into shrinking space. Entropy continues to climb, but now through concentration. Collisions grow more common, black holes merge into larger and larger singularities, radiation thickens the cosmic background. Disorder increases not by dispersal into emptiness but by intensification into chaos. The universe does not become more ordered as it contracts, it becomes more violent, more tangled, more extreme. This tension between the symmetry of physical laws and the asymmetry of entropy has long fascinated scientists. The Big Bang itself represents the lowest entropy state imaginable, a nearly uniform fireball from which all structure arose. In the vision of a big crunch, the universe ends not in simplicity but in complexity pushed to the breaking point, galaxies torn apart, black holes swallowing light, matter compressed until physics itself may fail. If the beginning was smooth and simple, the end is jagged and unruly. The idea of a perfect mirror, a universe rewinding itself, gives way to something less elegant but no less profound, a universe that folds back inward under the weight of its own chaos. This perspective also has deep philosophical consequences. Human beings experience time as a narrative, an unfolding story. If contraction does not reverse the arrow but instead accelerates our plunge into disorder, then the universe's future is not a replay but a crescendo. Every step toward collapse becomes a step deeper into transformation. History is not undone, it is amplified, burned into the fabric of the cosmos as entropy swells toward its maximum. To live in a contracting universe would be to witness not the erasure of memory but its echo, magnified against the shrinking backdrop of space. Yet the parallel between beginning and end cannot be ignored. The Big Bang and the Big Crunch form a kind of symmetry, even if the processes inside them differ. From one singularity of unimaginable density the universe blossomed outward, toward another, it may now race back. In this sense, time in a cosmic context may be cyclical even if our personal experience of time is linear. Civilizations could rise and fall within one expansion only to vanish as contraction carries all structures into collapse. Whether this cycle begins anew after the crunch is a question left to speculation, but the parallel haunts our imagination. The universe may be a story told not once but endlessly, with each telling shaped by the same bookends of beginning and end. For human beings, such thoughts inevitably raise existential concerns. If time itself is not reversed, then memory, identity, and history remain what they are, yet they exist in a cosmos hurtling toward compression. The future is not erased but darkened by inevitability. To know that entropy will continue its climb even as the universe shrinks is to recognize that our history is not just fragile but fleeting, an island of order in an ocean of collapse. And still, this recognition might also deepen our sense of meaning. In a universe where contraction mirrors creation, our brief moment of awareness becomes part of a larger rhythm, a pulse of time itself. The arrow of time, then, does not bend backward. It presses forward, through expansion, through contraction, through every transformation the cosmos can endure. But if it does not reverse, contraction ensures that its consequences grow sharper, its march more dramatic. Time may not reverse, but our history may echo forward. The announcement that the universe had begun to contract would ripple across the world with a force rivaling the greatest moments in human history. At first the news would be framed cautiously, hedged by scientific uncertainty, but once the evidence became overwhelming, no amount of careful language could soften its impact. Governments would convene emergency councils, universities would summon their brightest minds, and religious institutions would speak to their followers about the meaning of such a revelation. For some, contraction would be taken as a distant, almost abstract event, measured in billions of years and irrelevant to daily life. For others, it would be a looming catastrophe, proof that the end of all things had already begun. In government chambers, leaders would struggle to balance calm with urgency. On the one hand, they would be advised that contraction unfolds over vast timescales and poses no immediate danger to their populations. On the other, the symbolism of cosmic collapse would inflame public fears, forcing them to respond as though the threat were imminent. Policy debates would emerge about whether to invest in deeper space programs, in the search for new physics, or in technologies capable of protecting humanity from a future of escalating cosmic hazards. Some nations would pour funding into research, hoping to secure prestige by being first to understand or even manipulate the conditions of contraction. Others would see it as a distraction from earthly concerns, unwilling to allocate resources to something that might not matter for countless generations. Religious leaders would interpret contraction through the lens of their traditions. Some would call it the fulfillment of prophecies long foretold, the return of cycles of creation and destruction described in ancient texts. Others would present it as a challenge to human arrogance, a reminder of our smallness in a universe that bends to laws beyond comprehension. Still others would speak of renewal, of a collapse that could be followed by rebirth, offering comfort to those who feared annihilation. Across denominations, sermons, rituals, and gatherings would swell with attempts to place contraction in the context of divine will or cosmic justice. Among ordinary people, the emotional spectrum would be wide. Panic would take hold in some quarters, especially where sensationalist media portrayed contraction as an immediate apocalypse. Families might stockpile supplies, imagining sudden disasters, while conspiracy theories spread that the end was nearer than scientists admitted. At the same time, curiosity and awe would grow in others. Public lectures would overflow with audiences eager to hear what contraction means, and a wave of new literature, art, and film would emerge, inspired by the drama of a universe folding back upon itself. Fear and fascination would intertwine, shaping culture in unexpected ways. Scientists themselves would find their role changed overnight. Cosmologists, once a niche community, would become global figures, sought after by governments and media alike. Teams would scramble to refine models, desperate to predict the consequences of contraction with greater precision. Would certain regions of space remain stable longer than others? Could humanity migrate toward zones less affected by cosmic violence? The dream of escaping the universe altogether, through wormholes, parallel realities, or engineered bubbles of space-time, would shift from speculative fiction into serious theoretical work. Laboratories and observatories would be flooded with new funding, as if the future of civilization depended on their discoveries. The question of solutions would dominate discourse. If contraction could not be stopped, could it at least be delayed or mitigated? Some would propose that manipulating dark energy might offer a path, reversing its reversal and restoring acceleration. Others would argue for pragmatic survival strategies, such as spreading humanity beyond Earth before galactic collisions intensified. A few would call for humility, insisting that contraction is beyond our power to alter and that our efforts should focus instead on preserving culture, knowledge, and meaning while there is still time. The first responses, then, would be divided: fear and resolve, despair and curiosity, faith and skepticism all playing out simultaneously. Humanity has always responded to great upheavals in this way, with both paralysis and creativity, both retreat and advance. Contraction would be no different, except that its scale dwarfs all previous crises. For the first time, the fate of the universe itself would become part of the public conversation. In every parliament, every pulpit, every laboratory, the question of what contraction means and how to face it would rise to the forefront of human thought. Science and society brace for the next phase. At first the night sky would appear unchanged, a familiar canopy of constellations and scattered galaxies faintly visible through telescopes. For generations after the onset of contraction, no naked eye could distinguish the difference. Yet over time, the evidence would creep into view, subtle at first and then undeniable. The sky, once thought eternal in its design, would become a shifting panorama. The distant smudges of light astronomers identify as galaxies would grow brighter and larger, not because our telescopes had improved, but because those galaxies would truly be drawing nearer. Constellations, though defined by the motions of stars within our own galaxy, would remain recognizable, but beyond them the cosmic scenery would change in ways no human history had ever recorded. The first striking change would come from the local group, the small collection of galaxies to which the Milky Way belongs. Even in an expanding universe, we already expect the Milky Way and Andromeda to collide billions of years from now. In a contracting universe, this timetable would accelerate. Andromeda would appear larger in the sky much sooner, its spiral arms stretching across a swath of darkness. Eventually, its shape would no longer be the faint haze seen in telescopes but a looming structure that dominated a portion of the heavens. Over millennia, stars from both galaxies would mingle, glowing tides of light visible even from Earth's surface. What once seemed a cold, distant neighbor would become a luminous threat, pressing nearer with each passing age. Beyond our galactic neighborhood, other collisions would unfold. Clusters of galaxies, once separated by vast gulfs, would slide together. Astronomers watching with advanced instruments would record fireworks on unimaginable scales, galaxies merging, their gas clouds colliding to ignite furious star formation, their black holes colliding to release torrents of energy. These events, so rare in an expanding cosmos, would become increasingly common. From Earth, such collisions would appear as sudden flares in the night sky, bursts of brightness that grew and then lingered as tangled knots of stars. The sky would grow busier, brighter, more violent. Instead of receding into solitude, galaxies would fill the heavens with their dying beauty. The great voids that expansion had carved between them would shrink, replaced by crowded webs of matter. For future observers, the night sky would no longer be a quiet, static dome but a stage of constant transformation. To look upward would be to witness the slow-motion collapse of the cosmos itself. Yet beauty would accompany the dread. Imagine the Milky Way stretching overhead as it does now, but with another great spiral interwoven, the arms of Andromeda glowing against the stars of our own galaxy. Imagine regions of the sky punctuated by the bright knots of newly formed stars, dazzling blue clusters born in the chaos of galactic mergers. To human eyes, the heavens would seem alive with creation even as they heralded destruction. For poets and dreamers, such a sky might be the most awe-inspiring vision ever offered, a universe displaying its grandeur in the very act of falling apart. Still, the awe would be shadowed by fear. Astronomers would calculate the growing risks to planetary systems as galactic collision stirred gravitational chaos. Entire star systems could be ejected into intergalactic space, cast adrift without the warmth of a sun. Others might plunge toward black holes or be torn apart in close passes with neighboring stars. The very sky that dazzled with its brilliance would also be a reminder of humanity's precarious place in the cosmic drama. The spectacle would not be benign, it would be the visible symptom of a universe rushing toward collapse. For civilizations advanced enough to survive into this era, the sky would serve both as warning and inspiration. It would drive them to understand the mechanisms of contraction more deeply, to seek survival strategies against the inevitability of galactic turmoil. But it would also reshape their culture, their art, their sense of identity. How could anyone gaze upon a night filled with colliding galaxies and not be changed by the vision? To live beneath such a sky would be to live with the constant knowledge that the universe itself was closing in. The longer contraction continued, the more extreme the changes would become. Galaxies that once appeared as faint streaks would burn as luminous beacons. The sky might glow with a diffuse brightness as countless stars from merging systems crowded the heavens. Darkness would give way to radiance, a kind of inverted night where collapse illuminated everything. Eventually, the night sky would no longer offer quiet contemplation but a ceaseless reminder of the approaching end. And yet, there would remain a paradoxical sense of wonder. The contracting universe would not hide its fate in cold equations or distant calculations. It would display its transformation openly, visibly, spectacularly. Humanity, or whatever descendants might still exist, would not need mathematics to know the truth. They could simply look upward and see it written in the stars. And with the stars drawing together, so do their fates. As contraction deepens, the night sky would cease to be a quiet gallery of distant lights and instead transform into a theater of destruction. Stars that had once lived their lives in relative solitude would increasingly find themselves pulled into chaotic encounters. Galaxies rushing together would stir their stars into unstable paths, turning what were once tranquil orbits into deadly collisions. Where expansion had preserved distance, contraction would enforce proximity, and the heavens would respond in kind. The first and most dramatic consequence of this new closeness would be the collision of stars. While space remains vast and most stars would still avoid direct impact, the sheer density of contracting galaxies would guarantee that collisions occurred far more frequently than in the age of expansion. When two stars collided, their gases would merge violently, releasing bursts of light that could outshine entire galaxies for brief periods. Some stars would be torn apart, their remnants feeding the birth of new giants. Others would ignite in supernovae, detonating with the force of billions of suns, scattering heavy elements into their surroundings. For civilizations fortunate or unfortunate enough to witness these events up close, the spectacle would be both mesmerizing and lethal, flooding nearby systems with radiation. the contraction of space would also shorten the timescales of stellar evolution. Stars that might have quietly burned for billions of years could be forced into instability by gravitational disturbances from neighbors. Binary systems, already precarious in their balance, would be especially vulnerable. White dwarfs in close orbit with larger stars might more frequently accumulate matter past critical thresholds, triggering thermonuclear supernovae. These sudden blasts would lace the universe with light, leaving behind neutron stars and black holes, and adding to the growing inventory of cosmic hazards. If the stars were restless, black holes would be ravenous. Galaxies moving inward would bring their central black holes closer together, and eventually these titans would collide. The mergers of supermassive black holes would release gravitational waves of extraordinary power, rippling through space-time with an intensity far surpassing anything humanity has yet detected. Around them, the violent infall of gas and stars would create quasars, brilliant beacons shining across the collapsing universe. Black holes would no longer sit quietly in galactic hearts, they would dominate the cosmic landscape, feeding and growing with every encounter. As contraction advanced, they would merge into ever larger singularities, preparing for an ultimate coalescence when the cosmos reached its final stages. In this era of contraction, the energy budget of the universe would shift. Where expansion had steadily diluted light and heat into emptiness, contraction would concentrate it. Every stellar collision, every supernova, every feeding black hole would add to a rising background of energy. The cosmic microwave background, once faint and cool, would heat as contraction tightened space, while local bursts of radiation from catastrophic events would spike unpredictably. Space would no longer be a vast silence but a storm of energy, surging in waves of light, heat, and radiation. The stars, in their depths, would illuminate the path of collapse. To observers, the sight would be both beautiful and terrifying. Imagine skies lit by supernovae occurring not once in a generation but multiple times within a lifetime. Imagine galactic centers blazing with quasars so bright they rival the light of entire star fields. The night would no longer be dark, it would be punctuated by constant eruptions, flickering with the signatures of dying stars and merging black holes. To the human eye, the universe would appear more alive than ever, its brilliance unmatched in history. Yet this was not the light of creation but of destruction, the desperate radiance of systems tearing themselves apart. For any life still clinging to fragile worlds, the dangers would escalate. Radiation from nearby supernovae could strip atmospheres, sterilize surfaces, or trigger mass extinctions. Gamma-ray bursts from collapsing stars could sweep through entire regions, rendering them uninhabitable. Planets wandering too close to black holes would be ripped into streams of gas, their matter spiraling into accretion disks that shone like cosmic furnaces. The same contraction that made the universe dazzling would also make it hostile, pushing survival to the limits. The paradox of this epoch would be stark. On one hand, contraction would unleash creativity on an unprecedented scale, the birth of new stars from colliding gas clouds, the forging of heavy elements in supernovae, the assembly of black holes into giants of unimaginable mass. On the other hand, it would be a creativity inseparable from annihilation. For every new star born, many more would perish violently. For every black hole that grew, countless systems would be consumed. Creation and destruction would no longer be separate phases of cosmic history, they would become simultaneous, inseparable, and inseparably violent. Philosophers of this future era would find in the heavens a metaphor too powerful to ignore. The cosmos would appear as a place where brilliance comes only at the cost of collapse, where light itself is the signal of endings. In art and thought, the contracting sky might be celebrated as the ultimate union of beauty and doom, a reminder that even the grandest displays of the universe are transient. Civilizations that endured long enough to watch these fireworks would be forced to live with the knowledge that the brilliance they admired was also a countdown to the end. As contraction continued, the density of the universe would only increase, ensuring that these cataclysms multiplied. The collisions of galaxies would become routine, the merging of black holes expected, the sky ablaze with energies that no living eye could fully comprehend. It would be an age of unparalleled spectacle, the last flourishing of cosmic light before the final collapse. The universe grows brighter, but also shorter-lived. For much of its existence, the solar system has been shielded from the grand motions of the universe. The sun's gravity binds Earth and the other planets tightly, indifferent to the slow expansion of space. Even as galaxies drifted apart, our own small system remained stable, a pocket of order in a vast and restless cosmos. But contraction alters the larger environment in which the solar system is embedded. Though the pull of the sun continues to hold its planets, the surrounding galaxy will change, and with it the long-term fate of our home. The Milky Way, already on a collision course with Andromeda, would feel the tightening grip of contraction sooner than expected. The two galaxies would meet and merge long before they otherwise would have, transforming the sky into a tangle of stars. For the solar system, this merger would bring risks that had once seemed comfortably remote. The sun and its planets could be dragged into new orbits as the galactic structure rearranged itself. The chances of nearby stars passing dangerously close would increase, each encounter carrying the potential to disturb the delicate balance of our planetary system. A close stellar pass might tug comets from the outer regions of the solar system, hurling them inward in a storm of impacts. A stronger encounter could shift the orbits of outer planets, destabilizing the system and potentially ejecting smaller worlds into interstellar space. Even if Earth remained bound to the Sun, the gravitational turbulence of a contracting galaxy would ensure a future marked by instability. Stability, once taken for granted, would become an increasingly fragile condition. At the same time, the Sun itself would not remain constant. Independent of galactic events, it is already fated to exhaust its hydrogen fuel and swell into a red giant in roughly 5 billion years. Contraction would not alter this basic stellar evolution, but it might accelerate or complicate the timeline. Interactions with passing stars could strip material from the Sun or feed it fresh gas, destabilizing its equilibrium. Encounters with dense regions of the galaxy could bathe the solar system in radiation, weakening the protective shield of planetary atmospheres. In such an environment, the Sun's transformation from a stable star into an unstable giant could arrive in a less predictable, more violent way. For Earth, the prospects would grow grim. Even without cosmic contraction, our planet's long-term future is precarious. The Sun's gradual brightening is expected to render Earth uninhabitable within 1 billion years, boiling the oceans and sterilizing the surface. With contraction accelerating galactic hazards, this deadline might be shortened. A nearby supernova could blast the planet with radiation, disrupting its atmosphere. A gravitational disturbance could slowly stretch Earth's orbit until it drifts from the Sun's habitable zone. And in the chaos of galactic collisions, there is always the possibility, however small, that Earth itself could be thrown free, cast adrift as a frozen world wandering the void. Yet survival is not a simple yes or no. Life, once established, has shown resilience in adapting to extremes. Even if Earth's surface became hostile, subterranean environments or engineered refuges could harbor organisms for far longer. Advanced civilizations might adapt through technology, building shelters against radiation, or moving populations off-world to more stable environments. Moons, asteroids, or artificial habitats could serve as lifeboats against the turbulence of contraction. But each of these strategies would confront increasing risks as the universe grew more hostile. For civilizations beyond Earth, the situation would mirror our own. Across the Milky Way and its merging neighbors, planetary systems would face similar threats. Worlds would be lost to radiation, orbits would unravel, and countless planets would be ejected into interstellar exile. Those with the means to prepare would search for strategies to endure, but none could ignore the tightening squeeze of contraction. The solar system's story is just one among billions, each caught in the same inexorable motion toward collapse. What contraction reveals most clearly is that survival in a cosmic sense is not guaranteed by local stability. A planet may circle its star faithfully for billions of years, but in a universe rushing inward, no system remains isolated forever. The collapse of galaxies, the feeding of black holes, the rising radiation of the cosmos, these are forces larger than any star can resist. Earth's survival, like that of every world, depends not only on its own conditions but on the fate of the universe itself. The solar system, then, becomes a microcosm of the larger story. For a time, it may remain largely intact, its planets following familiar paths and its sun burning on. But as contraction intensifies, the forces of galactic chaos will intrude, eroding its stability until even this small island of order succumbs to the greater tide. Earth, with its fragile biosphere, stands at the center of this unfolding drama, a reminder that even home is not immune to the universe's shifting balance. And when worlds crumble, civilizations must choose. Civilizations, no matter how advanced, are born into a universe they do not control. For most of history, humanity has lived with the illusion that the cosmos is a backdrop, indifferent but stable, a stage upon which life unfolds. Contraction shatters that illusion. If the universe itself is collapsing, then the future of civilization becomes inseparable from the fate of space-time. The problem is no longer one of adaptation to climate, or technology, or even stellar evolution. It is the question of survival within a cosmos that is closing in on itself. The first challenge for civilizations is psychological. To know that every star, every world, every memory of history is destined to converge into a final singularity is to live under the heaviest of shadows. Some cultures might embrace this fate as a natural cycle, a cosmic rhythm beyond resistance. Others would rebel, pouring every resource into escape. Between resignation and defiance lies a spectrum of responses, some choosing to live as fully as possible in the time remaining, others sacrificing everything in the hope of extending existence. For those who refuse resignation, the question becomes, where can one go? The obvious solution, migration to another galaxy, fails in the face of contraction, for all galaxies are rushing inward together. To flee across space is only to buy time. The more radical proposals push beyond ordinary physics. One possibility is the creation of artificial universes, engineered bubbles of space-time, disconnected from the collapsing cosmos, that could serve as havens for life. Though entirely speculative, such concepts emerge naturally when faced with extinction on a universal scale. If our universe is collapsing, perhaps it is possible to create new ones, offspring universes seeded in laboratories, each potentially expanding forever while its creators watch their own world die. Another possibility is multiverse travel. If other universes exist, parallel to ours in some higher dimensional framework, then perhaps advanced civilizations could find or forge pathways to them. Wormholes, quantum tunnels, or technologies we cannot yet conceive might allow a migration not across galaxies but across realities. In such visions, contraction is not the end but a threshold, pushing intelligent beings to break through the walls of their own cosmos. Yet the risks are immense. There is no guarantee that other universes are habitable, or even accessible, and the attempt could consume resources better spent on survival within our own. The pursuit of survival raises ethical debates of enormous weight. Who gets to go, if exodus is possible? If only a fraction of a civilization's population can be carried into a new universe or artificial bubble, who decides which lives are preserved? The wealthy, the powerful, the chosen few? Or do societies attempt to randomize, to preserve fairness even in the face of annihilation? Such dilemmas could fracture civilizations, as groups argue over whether to focus on collective dignity in inevitable decline, or gamble everything on desperate attempts to escape. Even deeper ethical questions arise from the possibility of creating new universes. If a civilization can generate a pocket cosmos, do they bear responsibility for whatever forms of life might emerge within it? To create a universe is not only to save oneself but to unleash untold futures of other beings, who may themselves face suffering and extinction. The act of salvation could become an act of unintended creation, entangling the fate of many lives not yet born. Some would argue this is the highest duty, to ensure that intelligence continues in some form, even beyond one's own survival. Others would call it hubris, a final overreach of species unwilling to accept their place in the natural cycle of collapse. There is also the haunting possibility that we are not the first to face such a decision. If contraction has occurred before, in cycles of expansion and collapse, perhaps earlier civilizations reached the same crossroads. Some may have perished without resistance, others may have seeded new universes, and still others may even have crossed into ours, making us their descendants. The question of survival in contraction is therefore not only a practical one but a philosophical one, tying us to the unknown history of all intelligence that has ever arisen. For humanity, the contraction of the universe would demand a reckoning with scale. Against billions of years and forces beyond comprehension, our ambition seems small. Yet civilizations have never been defined by passivity. To face the collapse of the cosmos would be to summon all knowledge, all creativity, all unity toward the possibility of enduring beyond it. Whether through exodus, through creation, or through acceptance, the fate of civilizations under contraction is not predetermined. It is shaped by choices, by will, and by the courage to confront inevitability. And perhaps, in the end, the value lies not in whether survival is achieved, but in how civilizations meet the challenge. To accept annihilation with dignity, to create with responsibility, to strive even when the odds are absolute, these are the measures of meaning in a collapsing universe. Life, after all, has always been about finding purpose in a world it does not control. Contraction only magnifies the stakes, making the search for meaning both more urgent and more profound. But beyond survival lies the final endgame of physics itself. As contraction accelerates, the universe becomes unrecognizable to the descendants of the civilizations that remain. What was once a vast and spacious cosmos, in which galaxies drifted apart into silence, now surges inward with relentless momentum. Every structure, from clusters of galaxies to the fabric of space-time itself, is caught in the tightening spiral toward collapse. The scale of this transformation is difficult to imagine. Distances that once seemed infinite begin to shrink, and the tempo of cosmic events quickens as energy concentrates in ever smaller volumes. The first and most dramatic changes appear in the deep sky. Galaxies that were once faint smudges on the edge of observability blaze into visibility as contraction brings them closer. Collisions, once rare over billions of years, now occur with frightening regularity. Galaxies merge into sprawling, chaotic forms, their delicate spirals shredded by gravity into streams of stars. The darkness of intergalactic space dwindles as the night sky fills with clusters crowding together, each lit with bursts of new star formation triggered by the violence of collision. The beauty of this spectacle is undeniable, yet beneath it lies the dread of an accelerating collapse. With galaxies colliding, their central black holes are drawn toward one another, spiraling inward until they merge in titanic events. The energy released from such collisions is staggering, shaking space-time itself with gravitational waves of unimaginable strength. Where once a few such mergers occurred in isolated epochs, contraction ensures that black hole unions happen across the cosmos in overlapping symphonies of destruction. Each merger concentrates mass into fewer, larger singularities, leaving the universe increasingly dominated by the gravity wells of these monsters. In the late stages, black holes may number less than the galaxies that once were, their reign a prelude to the collapse of all. Meanwhile, the cosmic microwave background, the ancient afterglow of the Big Bang, no longer whispers its faint, frigid signal. Instead, contraction heats it, raising its temperature with every epoch. Once it was just a few degrees above absolute zero, a ghostly remnant of the beginning. Now it warms steadily, bathing the universe in radiation. As the cosmos contracts further, this radiation grows more intense, turning from a cold background into a fiery sea. Stars and galaxies shine brightly, but against this rising heat, their light begins to blur, overwhelmed by the background glow of a universe burning inward. Radiation does not simply illuminate, it destroys. As temperatures climb, molecular bonds that once formed the basis of chemistry falter. Even before galaxies themselves disintegrate, the environments that might shelter life are eroded by the relentless bath of energy. Planets lose their atmospheres, stars are stripped of their surrounding systems, and the very conditions that made stability possible vanish. Civilizations, should they still exist, find themselves besieged not only by collapsing structures but by the heat of the universe itself. No fortress, no artificial habitat, can resist forever against a rising tide that fills all space. The acceleration of contraction also alters the very geometry of space-time. The distances between objects shrink faster and faster, until vast expanses that once required billions of years for light to cross can be traversed in mere millions, then thousands. Horizons collapse inward, and the sense of cosmic isolation vanishes, replaced by claustrophobic proximity. Where once stars were separated by gulfs of emptiness, now they crowd together, their light blending into a near-unbroken glow. To gaze at the night sky in these epochs is to see not darkness studied with light, but light overwhelming darkness, a cosmos glowing like a furnace as it folds into itself. The destruction of galaxies is not uniform. Some are torn apart, their stars flung free, while others merge intact into increasingly massive conglomerates. Yet all roads lead to the same end, entropy and gravity guiding matter into fewer, denser states. In these final stages, supermassive black holes may dominate completely, their horizon swelling until they encompass vast fractions of what were once entire galaxies. The collisions of these leviathans release bursts of energy, but the overall picture is one of simplification, of diversity collapsing into homogeneity as the universe streamlines itself into ever fewer forms. For any observer still watching, the psychological weight of this transformation is immense. The sky no longer offers mystery or wonder, it offers inevitability. Every direction reveals destruction, every epoch accelerates decline. The sense of permanence, which once defined stars and galaxies, is stripped away. The universe has become a theatre of endings, each more violent than the last, all pointing toward a singular fate. And yet, amidst this grand collapse, questions persist. What lies at the heart of contraction? Is it truly a mirror of the Big Bang in reverse, or does some unknown law intervene before the final crunch? For those who endure these last ages, speculation becomes more than academic, it is a matter of whether existence itself can outlast collapse. The end seems inevitable, but is it truly final? As the universe races toward collapse, the question inevitably arises, is this truly the end, or merely a transition? Throughout history, cosmology has wrestled with the possibility that the universe is not a one-time event but part of a grand cycle. Theories of a cyclic cosmos suggest that the Big Bang may not have been the beginning of everything, but simply the latest chapter in an endless rhythm of birth, expansion, contraction, and rebirth. If so, then the Big Crunch might not signify annihilation but preparation for a new beginning, the spark of another universe emerging from the ashes of this one. The idea of a cyclic universe is ancient, woven into myths and philosophies long before science gave it form. In modern cosmology, it is most often captured in the concept of the big bounce. According to this vision, when contraction compresses space-time to its ultimate density, a reversal occurs. Instead of collapsing into nothingness, the universe rebounds, expanding once again in a new Big Bang. In this model, our universe is neither eternal in its current state nor terminal in collapse, but part of an infinite chain of universes, each rising and falling in turn. The Big Crunch becomes a gateway rather than an end. For such a bounce to be possible, physics must behave differently at the extremes of density and temperature. Classical general relativity predicts a singularity, a point of infinite density and curvature, where laws of physics break down. But quantum cosmology suggests that new principles emerge at such scales. Quantum fluctuations, vacuum energy, or unknown aspects of space-time geometry may prevent a true singularity from forming, halting collapse at the brink and igniting a new expansion. Just as quantum physics saved the atom from collapse under classical mechanics, it may save the universe from vanishing into nothingness. In some versions of the theory, the new universe carries echoes of its predecessor. Information from the collapsing cosmos might be imprinted in the conditions of the reborn one, subtly shaping its fundamental constants or structures. If so, our universe itself could bear traces of countless previous cycles, encoded in the patterns of cosmic radiation or the distribution of galaxies. Each universe would thus be a child of the last, inheriting whispers of its ancestry across eternity. In other versions, the bounce erases history entirely, producing a truly new cosmos with no memory of what came before. The question of continuity, whether the next universe remembers us, becomes as profound as the question of whether it exists at all. Beyond the big bounce lies the even broader idea of the multiverse. Perhaps contraction does not lead to one new expansion but to many, with a collapsing universe fragmenting into a foam of newborn universes, each with its own laws of physics. Or perhaps contraction delivers our cosmos into contact with others, passing through a transition where boundaries dissolve and new realities emerge. In such a vision, the Big Crunch is not a solitary end but a branching of possibilities, a flowering of worlds beyond imagining. The death of one universe becomes the birth of countless more. These theories, while speculative, offer a counterpoint to despair. If contraction is not annihilation but transformation, then the story of the cosmos is not tragic but eternal. Even if civilizations within this universe cannot survive the transition, their existence may have played a role in shaping what comes next. Just as stars must die to seed galaxies with heavy elements, perhaps universes must collapse to seed the birth of others. In this way, every act of life, every thought and creation, becomes part of a chain that extends beyond comprehension, influencing realities yet unborn. The scientific community remains divided on these questions. Some argue that there is no evidence for cyclic models, that contraction leads only to silence. Others believe that hints of previous cycles might already be encoded in the data we observe, waiting for interpretation. Quantum gravity, still incomplete, may eventually offer clarity, bridging the gap between collapse and rebirth. Until then, the theories remain both a comfort and a challenge, proof that even at the edge of everything, imagination and inquiry persist. To believe in rebirth is not to deny the terror of contraction but to frame it within a larger horizon. The idea that death and renewal are inseparable is a familiar one in life, echoed in the cycles of stars, of ecosystems, even of human generations. If the universe itself participates in such a rhythm, then our place within it may not be to resist its collapse but to recognize our role within the eternal dance of creation and destruction. If the end is also a beginning, what role do we play? As the universe contracts and the end draws nearer, civilizations, whether human or alien, would be forced to confront questions that are no longer abstract philosophy but urgent reality. If all things are destined to collapse into the Big Crunch, what does meaning become? Does it matter that knowledge, culture, and memory were ever created if nothing survives the final collapse? Or is the act of creation itself enough, regardless of permanence? These questions would echo through every hall of philosophy, religion, and science, as the cosmos itself became a mirror forcing beings to look inward. The effort to preserve knowledge would not stop simply because survival seemed impossible. Humanity, and perhaps others like it, has always sought to resist forgetting. Just as ancient civilizations carved their myths into stone, so too might advanced beings carve their truths into the fabric of space-time itself. Time capsules might be built not for the Earth but for the universe, designed to last as long as possible in the face of growing heat and contraction. Some might turn to signals, broadcasting messages across shrinking galaxies in the hope that something, somewhere, someone, might hear them before silence descends. Others might turn to artificial intelligence, crafting entities that could adapt and endure longer than their makers, even if endurance itself has limits. Such efforts would embody defiance against inevitability. Even knowing that contraction may erase all traces, civilizations might persist in recording themselves, for the act of leaving a mark is inseparable from what it means to be intelligent and self-aware. The value lies not only in whether a message endures but in the decision to create it. In this way, legacy becomes less about permanence and more about intention. To preserve memory is to declare that life mattered, that consciousness arose, and that it left something behind, however brief in the scale of eternity. The existential weight of contraction would bear down in countless ways. Some would despair, seeing futility in every endeavor. If galaxies, stars, and even atoms are destined to vanish, then what is the point of art, science, or love? Yet others would find the opposite, an urgency that makes every moment more meaningful. If time is finite, then each experience becomes infinitely precious. A poem written before the end, a gesture of kindness, a scientific insight, they gain significance precisely because they cannot last. To live with awareness of collapse is to live fully in the present, knowing that the present itself is all that can ever truly be. Civilizations might split along these lines. Some would embrace nihilism, retreating into despair or hedonism as contraction advances. Others would turn to ritual, art, and exploration, driven to make their last era one of flourishing rather than silence. The meaning of existence would no longer rest in the distant hope of continuity but in the immediacy of expression and connection. Legacy would shift from the attempt to outlast the universe to the attempt to affirm life even as it slips away. In the end, perhaps the question is not whether memory survives contraction but whether memory existed at all. The universe once had no observers, no minds to reflect upon it. That it came to host beings capable of wonder is itself extraordinary. If contraction erases all evidence of those minds, it cannot erase the fact that they once were, that the cosmos briefly knew itself through them. That realization may be the deepest legacy of all. Even as stars fade, the question of legacy burns bright. In the last moments of a contracting universe, the cosmos no longer resembles the one that was once vast and silent. The sky, once a tapestry of scattered stars against infinite darkness, becomes a blazing ocean of light and fury. Galaxies have already merged into monstrous, glowing masses. Black holes have swallowed much of what once drifted serenely across the void. Now, all is pressed together, every source of matter and energy rushing inward under gravity's irresistible call. The night sky has vanished, replaced by a dome of fire in every direction, as if existence itself has been set aflame. The airless expanses between worlds are no longer empty. Radiation saturates everything, flooding through space in a relentless tide. The cosmic microwave background, once the faint afterglow of the Big Bang, has brightened into a furnace, rising from cold whisper to searing roar. Heat climbs without end, as contraction drives energy into smaller and smaller spaces. The fabric of the universe feels less like a stage for existence and more like a crucible, burning away what remains. Stars, planets, and life itself become indistinguishable beneath the overwhelming tide of light and heat. On smaller scales, destruction grows intimate and terrible. Atoms, once stable, begin to fail. Electrons are stripped away as radiation intensifies, leaving behind bare nuclei that themselves are battered by forces beyond endurance. Fusion, the engine of stars, becomes meaningless in this maelstrom, for matter itself is unmade in the rising inferno. The familiar building blocks of chemistry, of biology, of everything once known, dissolve into pure energy. The distinction between matter and radiation blurs, until all is only a violent glow hurtling toward collapse. And still contraction accelerates. Distances that once took millions of years for light to cross are now compressed into spans so short that horizons fold in upon themselves. The universe shrinks not only in scale but in time. The rhythm of events that once played out across eons now beats in frantic succession. Black holes, swollen with the remains of galaxies, spiral toward one another in catastrophic mergers, their horizons colliding, their singularities fusing. Each collision unleashes torrents of energy, but there is no longer room for the waves to propagate freely. Space itself is too small, too compressed, and every outburst only hastens the collapse. To any observer still conscious in these final instants, the sky is no longer a place of beauty but of unbearable intensity. There is no darkness left, no stars as individual points. The whole of creation blazes as one, a ceaseless storm of radiation and matter stripped of form. There is no safe distance, no sanctuary from the convergence. It is as though the cosmos itself has become a single fireball, raging against its fate yet unable to resist it. The awe is inescapable, mingled with terror, an ending at once sublime and merciless. Space-time itself begins to yield. General relativity, which for so long described the dance of planets and galaxies, now predicts only a singular outcome, the crushing of all dimensions into a point of infinite density. In these last stages, geometry loses meaning. Directions collapse into one another, time itself, once a steady current, becomes turbulent and fractured. What does it mean to speak of before and after when intervals vanish into infinitesimal fragments? The arrow of time, so deeply tied to expansion, seems to fray as contraction folds it back upon itself. The universe, once vast and ancient, has aged into a heartbeat, pulsing once more toward silence. The emotional gravity of this moment is overwhelming. For beings capable of reflection, to witness the end is to face the deepest paradox. Everything they cherished, from the smallest memory to the grandest achievement, is erased, and yet the spectacle of that erasure is itself magnificent. Civilizations may weep, may sing, may record their final thoughts, but all such acts dissolve into the glow. The universe becomes its own requiem, a final symphony of fire, gravity, and collapse, echoing with no one to hear. And yet, within the crushing inevitability, hope lingers. Perhaps quantum laws will intervene before the singularity, sparking a rebound. Perhaps contraction will not conclude in silence but in renewal. For those who dream, the fire is not only an ending but a womb. They imagine the possibility that what now collapses into darkness will ignite once again into light, birthing a universe anew. In this vision, the final glow of collapse is not death's flame but the seed of another dawn, a cycle stretching beyond comprehension. The final moments are indescribable not because they lack detail, but because detail itself dissolves. There is no longer a sky, no longer stars or galaxies, no longer matter or radiation as separate things. There is only everything, compressed into one. The grandeur of billions of years is condensed into a single instant, an instant that holds all history, all memory, all meaning, collapsing together. It is the climax of creation and its undoing, the point at which existence itself holds its breath. And then, silence, or renewal. The end of the universe, whether envisioned as final silence or as the spark of a new beginning, is not simply an abstract scenario for physicists to debate. It is a mirror held up to existence itself, forcing reflection on what it means to live, to create, and to leave traces in a cosmos that may not preserve them. The contraction of the universe is more than a physical event. It is a story of meaning, of endings, and beginnings entwined in ways that defy simplicity. To speak of an epilogue is to acknowledge that endings always give rise to questions, and in those questions, something new is born. If the universe is cyclic, if collapse and rebirth form the heartbeat of eternity, then the story of existence is not one of loss but of rhythm. Creation and destruction become partners in an endless dance, each necessary for the other. Just as stars must burn out to seed new generations of worlds, perhaps entire universes must collapse to make way for the birth of new ones. In that vision, nothing is truly lost, even if no individual memory carries over. The legacy of life, of thought, of wonder, may not be preserved in detail, but the very fact of existence reshapes the conditions of the next cosmos. In this way, everything that was becomes a hidden thread woven into the tapestry of what will be. If, instead, the end is final, then its lesson is no less profound. Impermanence does not diminish meaning, it intensifies it. Knowing that the universe itself is finite urges one to treat each moment as a treasure. It reminds us that beauty and love matter not because they endure forever but because they happen at all. The awareness that even galaxies cannot last forever humbles human ambition but also elevates human experience. To create art, to explore, to seek understanding in a fleeting cosmos is an act of defiance against oblivion. For humanity, or for any civilization, the lesson of contraction is not despair but perspective. We may not control the destiny of the cosmos, but within our limited span we hold the power to shape meaning. The contraction of the universe challenges us to ask whether we live for permanence or for presence, whether legacy lies in what survives or in what is expressed while it can be. If all universes end, then what matters most may be how we inhabit our fragile window of time. And there is another lesson, too, humility before the unknown. The fate of the universe is not settled. Science continues to uncover new possibilities, from dark energy's mysteries to the role of quantum physics at cosmic extremes. We do not yet know whether the cosmos will expand forever, collapse into silence, or be reborn in infinite cycles. That uncertainty is not a failure of knowledge but an invitation to wonder. To imagine the universe collapsing and renewing is to glimpse the scale of questions that exceed us, and in that glimpse we rediscover awe. Even as contraction looms in speculation, the very act of asking what it means testifies to something extraordinary. The universe has produced beings capable of looking at it, of questioning it, of dreaming about its end. Whether or not those beings survive contraction, whether or not their memories persist, the fact of their awareness is itself a wonder no collapse can erase. For as long as thought exists, the universe is not only matter and energy but also reflection, meaning, and story. So the epilogue is not closure but opening. The end of a universe, imagined or real, points beyond itself, to cycles and mysteries that remind us that we will never have the last word. Even if silence comes, it is not emptiness but a silence that contains the possibility of another beginning. And if renewal comes, it is not a return to the same but the birth of something unimagined, carrying within it the hidden echoes of everything that was. From ending to beginning, from collapse to creation, the cosmos is both fragile and eternal. Its story is our story, whether brief or unending. To wonder about its fate is to wonder about ourselves, and in that wondering lies the essence of what it means to be alive. The universe may end, but wonder does not. The last lesson of contraction is that endings are never only endings, they are doorways, thresholds, horizons. And in stepping across them, we are invited to imagine what lies beyond.